I want to do the linear air resistance velocity equation that we actually derived in class yesterday. And so we have an object that is falling in the presence of air resistance. So we have an air resistance force going up, and we have the weight of the object pointing down, and we'll say that the air resistance is equal to negative kV, the weight is equal to mg. And we're going to kind of ignore where the arrows point. And the way we set up Newton's second law for this system is that we actually write mg minus kV equals m times a. And of course, in this situation, what we're saying is that downwards is the positive direction. Now, I'm going to do this a little bit quicker than I did in class, just to get through the mechanics of it so you can study this for the quiz tomorrow. But here's the idea. Mg minus kV equals ma, and we're going to actually convert a to a derivative, specifically the derivative of velocity. And now what we've done is we've obtained a differential equation that we want to solve for v as a function of time. Now, one of the conditions that we're given, the initial condition, I'll abbreviate that as IC for initial condition, is that v of 0 is 0. So at time equals 0, the object is not moving. So now what I'm going to go and do is I'm going to actually use the method of separation of variables. And what that means, as I said yesterday, is that we're going to put all the dt and t stuff on one side and all the v and kv stuff on another. And another thing I want to emphasize is that mass, gravity, the air resistance constant, the drag coefficient as it's called, are all constants. We treat them like they are numbers, with a little bit of a twist, which is that we're going to do just a small bit of algebra with them to make sure that the calculus we want to do comes out as simple as possible and as easy to manage as we can make it. So we're going to have, I'm going to multiply both sides by dt, and then I'm going to divide both sides by mg minus kv. And so I'll divide this side by mg minus kv as well, and we have some cancellation. So what I'm ultimately going to be left with is the equation dt over, dt equals m dv over mg minus kv. And we're going to want to integrate both sides. Okay. And the way we're going to do this is we're actually going to do a u substitution. So we're going to say u equals mg minus kv. And keep in mind, this is a constant and this is a constant. So we're going to have du equal to 0 minus k dv, or in other words, du over negative k equals dv. So this is our u. And then this is our mg minus kv, which is u, and then this is our dv, and then we can substitute back into this equation. And what we're going to get when we substitute, let me just shrink this a little bit, is we're going to get an equation that we can solve, that we're going to eventually integrate, and that's going to be dt equals, and we will write this as u du over u, and we're actually going to have an m here from before. We're going to have the m from before, and we're going to divide by 1 over negative k, which comes from this thing here. And so when we simplify, I'm going to simplify this to something that's easier to integrate. So we're going to rewrite this equation as negative k over m dt equals the integral of 1 over u du. So when we integrate both sides, we're going to get negative k over m times t equals natural log of u plus c. And now I can actually substitute my expression back in, and I'm going to do that on the next page here. So I'll take this, I'm going to flip pages. Let's just paste this here. And we'll move it up like that. And now we're going to put in our expression. Remember, let's remember that u is mg minus kv. I'll substitute that back into here. And I also want to remind you that v of 0 equals 0. So at t equals 0, v equals 0. Let's take all that into account. So we're going to say negative kt over m equals the natural log of mg minus kv plus c. Basically, we're going to use this to solve for c. And so that's going to be negative k times, and let's just do that on the side here. So negative k times 0 equals the natural log of mg minus k times 0 plus c. And so when we isolate c, we get 0 equals natural log of mg plus c. So it turns out c is equal to the natural log of mg, and we can actually substitute that back into here. So we'll say negative kt over m equals the natural log of mg minus kv minus the natural log of mg. Now let's use a little bit of natural log algebra. So negative kt over m equals the natural log of mg minus kv over mg. And now what I'm going to do is I'm going to take e to the both sides and simplify. I can't talk today. So then we have e to the negative kt over m equals mg minus kv over mg. I'll multiply both sides by mg. And so continuing over here, I'm going to get mg e to the negative kt over m equals mg minus kv. I'm going to isolate v by subtracting mg and dividing by negative k. And so what I'll end up getting is mg over k minus mg over k e to the negative kt over m minus mg equals negative kv. We're almost there. I'm going to factor, and I'm going to simplify just a little bit more. And when I do that, I'm going to end up getting here mg over k, 1 minus e to the negative kt over m equals v as a function of time. And this is the expression that we wanted to obtain for velocity as a function of time.